Hey, good afternoon, everyone. Hopefully you can all hear me. My name is Kevin Cahill. I'm a principal here at Interface Engineering. Welcome to Interface Engineering's 2025 Educational Webinar Series event, Geothermal Systems, a well-grounded conversation with Joe Daino. We are using a GoToWebinar meeting platform. If you wouldn't mind, just let me know in the chat if you can or can't hear us. Give us a thumbs up or something. I just want to make sure the audio is good with everybody. Not everybody, but if I see from some of you. Today's presentation will be recorded and made available through our website for future reference. All audience microphones are muted during the presentation. We'll open them up for Q&A at the end. Feel free to enter your questions in the questions field on the right-hand side, and we can address those as we go and certainly address them at the end. Interface Engineering is an approved AIA continuing ed service provider. You will earn 1 learning unit for this presentation. Attendees will receive a course completion certificate, and if we have your AIA number, that gets reported to AIA for you within the next couple of weeks. We'll allow a few minutes at the end so that you can ask questions of Joe. If we don't get some posted questions, we can always distribute the Q&A to everyone as well. So right now, I'll turn it over to Joe. Joe's a principal here in Washington, D.C. office of Interface Engineering. Joe has a master's in architectural engineering from Penn State University. Happy to have known Joe for, embarrassed to say, Joe, plus or minus 20 years now. Joe, it makes us both old, I suppose. But Joe's been here with us in Interface plus or minus 10 years, and has done extensive work with our organization with geothermal systems. So with that, Joe, I will turn it over to you.
Great, thank you, Kevin. Appreciate the intro, and welcome everybody to our 2025 High Performance Building Educational Series. I do have to give a hat tip to Roger Frechette, who was never one to miss out on a good pun with today's meeting titled Geothermal Systems, a Well-Grounded Conversation. So thank you, Roger. Right, we will get started here. So first, we'll do a little bit of housekeeping, talk about Interface, give you a little brief firm overview. Interface Engineering is a mechanical, electrical consultancy. We are active in many different market sectors, as you can see here. Workplace, science, technology, we do a little bit of everything. So our services include traditional mechanical, electrical, plumbing design. We also provide fire life safety services, lighting and daylighting, building services modeling, energy modeling. We also have building technologies, ABIT security, and we also do commissioning. So one of the things that we like to pride ourselves on is our focus on sustainable design. You know, here at Interface Engineering, we like to work on projects that are sort of on the cutting edge of sustainability, and we don't treat it as just a buzzword. It is something that we, actively try to pursue in all of our projects. We have done many LEED projects, many LEED Platinum projects, and also net zero energy and water projects as well. We have offices all over the United States. I like to say that we cover just about every time zone within the United States, from the East Coast, West Coast, and everywhere in between. So another housekeeping item, just we want to make sure that everybody is able to ask questions, and I will try to get to as many as I can at the end of the presentation. If you're using the web version, the little screen capture here on the left shows the question mark button. You can click that button and then enter in your questions. If you're using the desktop version of the app, there's a little vertical bar that you can expand, and you'll see a questions tab towards the bottom. I would suggest clicking the little square icon to undock the the questions part from the control panel. It makes it a little bit easier to see everything and to enter your questions in there. All right, so let's jump into the course description. Again, thank you for joining today. I know that everybody's time is valuable, and we appreciate when everyone can log on. So today we're going to talk about, what is a geothermal HVAC system and how do these work. We'll talk about some of the different types and how they're designed, and we'll look at some advancements in the industry as well. So as this is an AIA accredited course, we have to have distinct learning objectives, which today, again, it's to understand what geothermal HVAC is all about, learn about the benefits, the different types, how we go about designing these systems. And again, we'll look at some industry advancements in geothermal HVAC system design and construction. So the agenda, we'll go through what is a geothermal system, the types, the benefits, system design, and then advancements, and then we'll wrap up with questions at the end. So let's dive right into it. What is a geothermal HVAC system? So generally, the concept is it's an HVAC system that is utilizing the relatively constant temperature of the Earth to heat a building in the winter and cool it in the summer. One of the differentiators between a geothermal system and, say, a traditional system is that unlike traditional systems where we may be relying on fossil fuels and electricity from the grid, a geothermal system looks to harness renewable energy from the ground. So I have two images here on the right. In the top right corner, we have kind of an overlay of deep ground temperatures in the United States. So you can see the further north you are in the United States, you have lower numbers and then larger numbers as you go further south. And that really just represents the different climates and geology throughout the country. What makes geothermal interesting is that when you start to get a little further below grade, the chart in the bottom right-hand corner shows that, as you are going down below the Earth's surface, the ground temperature starts to stabilize, and a geothermal system is really trying to tap into that. So how does it work? Hopefully these images aren't too complicated, but it's the best that I thought I could provide so that everyone can get an understanding of how these systems work. So for a geothermal HVAC system, you really kind of have two components. You have the components that are inside the building and the components that are outside the building. So typically, a geothermal system is going to rely on some source of a heat pump inside the building to either reject heat into the ground when you're in a cooling mode of operation, or to absorb heat from the ground and bring that into the building when you're in a heating mode of operation. And again, the heat pump technology, which we'll talk about a little further later on in the presentation, is critical because that's going to be the means of how we're extracting the energy from the building and transferring it into the ground. So what are some of the components of a geothermal HVAC system? We're going to hit four major topics when we're talking about the components of the system. The first is going to be what we refer to as the ground loop heat exchanger. You may hear of that called a geothermal field or a geothermal bore field. Those are all sort of the same thing, with ground loop heat exchanger being kind of the technical terminology. We'll talk about the hydronic pumping system that is required to transfer energy from the ground into the building. We'll talk about centralized heat pump HVAC equipment and also distributed heat pump HVAC equipment, those being sort of the two approaches that you can take to implement one of these systems in your building. So the first item that I wanted to talk about is the ground loop heat exchanger itself. I have 6 versions here. These are the more common. There are actually more than this, but for the sake of brevity, I wanted to focus on these being kind of the ones that you're seeing the most in the industry. They're separated into sort of 2 types, both the open loop type and the closed loop type. Open loop would be your groundwater well, or a well and a surface body type application. And then closed loop types could be a pond or a lake application, a horizontal closed loop, another variety of the horizontal closed loop called the slinky, or the vertical closed loop system. So let's take a closer look at these different types. First, we'll talk about the open loop groundwater well. So this is the type of geothermal heating and cooling system that is directly pumping groundwater from a well into a building to do heat transfer via that fluid. So this is a little bit different because it is an open system that you are actually taking groundwater out of the ground, sending it into a building, either extracting energy from that or rejecting energy from that, and then putting it back into a separate well, which we call a discharge well. And typically those 2 wells are going to be a significant distance from each other so that you don't get any sort of cross-contamination. You would not want to be rejecting heat back into the ground and then it sort of recycle right back into your source well. So obviously this type of system is only going to be viable when there's a readily available and plentiful water source. There are environmental concerns with these types of systems because, again, you are directly taking groundwater out of an aquifer and bringing it into a building. We get fairly consistent groundwater temperatures with this type of system because, again, you're usually digging a well relatively deep where the groundwater temperature is going to be very stable. As it is sort of brackish water that you're pulling directly out of the ground, these types of systems are prone to fouling and corrosion on the indoor equipment. So filtration for a system like this is really critical. Another type of open loop system is what we call a well and surface body system. So it's very similar to the previous example, except in this case, you're trying to utilize some sort of open body of water adjacent to your building to either reject heat into or extract heat out of. Again, you can have environmental concerns with these types of systems as they are sort of open loop. These types of systems tend to have slightly less consistent groundwater temperatures, and really that's based on the fact that you have an open body of water, and depending on the depth of that body of water, can be very sensitive to ambient conditions. And again, as you are pulling water directly out of the ground or a surface body, these systems can be prone to fouling and corrosion. So filtration and chemical treatment is very important. Let's talk a little bit about closed loop systems. And when I say closed loop systems, it really means that the geothermal heat exchanger itself is a closed hydronic loop. You are transferring energy through various mediums. In this case, it would be a lake or a pond, but you're not directly extracting the water from that medium. So typically these types of systems are, coiled plastic piping that is then submerged into a body of water. They require close proximity to a body of water. If it's too far away, it's not really feasible to utilize this type of an approach. And again, you get less consistent water temperatures, geothermal closed loop water temperatures, that is, because again, depending on the depth of the body of water that you are submerging the piping in, it can be prone to temperature swings depending on ambient temperatures in the climate that you're in. Another type of closed loop system is the horizontal closed loop. Sort of like the name implies, you are simply circuiting plastic piping in a horizontal manner in a fairly shallow trench, typically around 4 to 6 feet deep. Some of the drawbacks of the horizontal system type is that it does require a significant amount of available land. So you are going to be limited in terms of, if you have a very large capacity, you would need quite a large plot of land. The shallow depth does help reduce the cost and complexity of these types of systems because you do not have to dig quite as deep as some of the other systems we'll talk about later. But again, because it is a shallow system, you get slightly less consistent water temperatures in a horizontal arrangement. The slinky, which is quite aptly named because as you can see here in the image, it does basically just look like a slinky that has been stretched out and laid down horizontally. The reason you would use this type of system is really just to gain a little bit of extra capacity. The slinky allows for a lot more heat transfer in the horizontal ground loop. And again, it's utilizing the same sort of shallow depth, which can help reduce the cost and reduce the complexity of this system type. And you're going to get slightly less consistent water temperatures based on the climate as well, because it is not buried that deeply into the earth. And finally, the last closed loop system I want to talk about, and probably the one that people may be slightly more familiar with, this is one of the more common types of ground loop heat exchanger applications, is the vertical ground loop. These are typically used where space is more limited and horizontal loops are not really practical. So you would install a vertical loop by drilling, essentially. So you're typically drilling several hundred feet vertically into the ground and then putting your geothermal loop into that borehole. Typically, these systems are multiple boreholes connected into a circuit and then multiple circuits connected horizontally back to the building. So what does a vertical geothermal borehole look like? So here you can see the image on the far right shows what we call the U-tube heat exchanger, or the U-bend heat exchanger, typically made out of high-density polyethylene pipe, or HDPE pipe. That pipe is going to be a closed loop filled with either water or a water and antifreeze mixture. The antifreeze comes more into play when you're in colder climates that are going to experience lower ground loop temperatures, and you have to add an additive to the water to make sure that it does not freeze. So typically we are drilling geothermal boreholes fairly deep and then inserting the U-tube into effectively what is a grout sort of substrate. And the grout is thermally enhanced, and it is what its purpose is trying to transfer the energy from the ground loop into the adjacent ground. The benefits of a vertical system, again, it reduces the total area required based on your capacity, and it's less likely to be affected by the temperature fluctuations at the surface because you are going deep into the ground. So another component of a geothermal HVAC system is the hydronic pumping system. So each of these systems has to have some means of transferring the fluid from the geothermal source into the building for heat exchange. There's a lot of different ways that you can do this on smaller projects, and even for some larger projects, you can take, for instance, in a closed loop source, you may just simply be pumping through the geothermal system and then taking that directly to your indoor HVAC equipment. In other cases, specifically where the geothermal loop requires the use of an antifreeze like propylene glycol, oftentimes we will separate that ground loop from a building loop using heat exchangers. Both applications are perfectly suitable, and really you just have to look at the specific requirements and constraints on your project to figure out which hydronic pumping system is most appropriate. So let's talk about the equipment then that gets placed inside of a building that is paired with the ground loop heat exchanger. So one approach is to look at more centralized HVAC equipment. And we say centralized, that would be like the image in the top left corner, basically a ground source heat pump air handling unit. They can be large scale air handling units, VAV air handling units. So the distribution within the building may be very similar to VAV distribution that a lot of people have seen in commercial office buildings and other types of applications. The difference being that it's not a chilled water, hot water system with a cooling tower and a boiler. We're using the ground source loop directly to transfer energy. Other centralized HVAC system equipment types include heat pump chillers. So in the top right corner, you see an example of a heat pump chiller. These are typically found in fairly large applications where you have a pretty substantial building heating and cooling load. These heat pump chillers are capable of producing both chilled water and hot water, and capable of energy recovery from the production of chilled water to put that energy directly back into the hot water stream. Another type of application is the modular water-to-water heat pump. So these systems are sometimes referred to as six-pipe chillers or six-pipe heat pumps, effectively have a cold loop, a hot loop, and a source loop. And the source loop is going to be your geothermal loop. These systems are also capable of producing chilled water, hot water, or simultaneously creating both chilled water and hot water. Another approach is the use of distributed HVAC equipment. So this is effectively, either vertical or horizontal ground source heat pump units. And these would be distributed throughout the building. Oftentimes you would see this type of an application in, say, a multifamily building or potentially a school type building where you have individual heat pump units in every zone throughout the building, and you're taking the fluid through the ground loop heat exchanger and then pumping that directly to equipment that is distributed throughout the building. Again, both the centralized and distributed HVAC equipment applications can be suitable. It really just depends what the specifics are for your particular project to know which system is going to be the right one to use. So let's look a little bit at the benefits of a geothermal HVAC system. Why would we go to all this trouble to create a ground loop heat exchanger and use that as part of our system? So firstly, we want to talk about energy efficiency. And this has always been sort of the hallmark of a geothermal system, is that it's going to provide substantially better energy efficiency when compared to other traditional applications. So most geothermal heat pump systems are going to have a COP, or a coefficient of performance, between 3 and 4.5. And what that means is that for every unit of energy that you're using to power the system, you're actually getting 3 to 4.5 units supplied as heat. When you compare that to a fossil fuel furnace or boiler that may be anywhere from 78 to 90% efficient, a geothermal heat pump is going to be about 400% efficient, right? So we're getting substantial benefit from an energy performance standpoint. There's also cost savings associated. Now, the initial installation cost is going to be higher for this type of a system. Again, there is the added expense of the ground loop heat exchanger, but the general idea is that because the system is so much more efficient, that your energy costs are going to be much lower, and that energy cost benefit will offset the initial higher first cost. Obviously, there are pretty massive environmental benefits when you're thinking about geothermal systems. Again, the geothermal system is going to effectively replace traditional forms of heat rejection, which may be a cooling tower that is going to use a considerable amount of water. And it can also replace boiler systems that are using natural gas, fuel oil, other types of sort of fossil fuel applications. So, there's a lot of information out there to sort of the sustainability benefits of geothermal systems, but to kind of put it in some context, putting these systems in a typical home could be the equivalent of planting an acre of trees, or even the equivalent of taking 2 cars off the road. So 2 cars might not sound like a lot, but when you think about how many homes there are throughout the country, if more homes were sort of tapping into the benefit of a geothermal system, it can have quite an impact on the environment. Another sort of benefit that is maybe not discussed as much is the longevity of a ground loop heat exchanger specifically. So oftentimes the equipment inside of the building is going to last anywhere from 15 to 25 years, but the ground loop heat exchangers themselves are really built to last 25, 50, sometimes even in excess of 50 years. So the investment is definitely something to look at from a long term. You're going to have this system available to you for, potentially the life of the building. So now we talked a little bit about the benefits and the different types of systems. Let's dive into the design of a geothermal HVAC system. So we're going to touch on 4 key areas here. The first being heating and cooling load calculations. The second, formation thermal conductivity testing. Then we'll talk about ground loop heat exchanger modeling. And then finally have a brief discussion on sort of the design documents. How do we get one of these systems built? So the load calculation portion of the HVAC system design is actually extremely critical. I mean, the load calculation portion of any design is going to be critical, but for geothermal, you really have to drill down very deep. And it's not just the peak loads that you may find, what is the peak cooling load, 100 tons, what is my peak heating? We're not necessarily looking at just one state point in time when we're looking at these loads, but we're looking at how does the building perform annually over the entire year. One of the things to be careful of with the design of a geothermal system is, oftentimes when a project is still in a conceptual stage, you may not even have architectural drawings. You just, have a general idea for what the building is and the size. Sometimes you'll hear, the idea of, well, how many tons per borehole am I going to get from my geothermal field? It's okay early on to sort of make these kind of estimates, but the one thing is to keep in mind that we're not really looking so much at how many tons per borehole, but how many ton hours, right? What is the annual aggregate sort of load that you're dealing with? I find that one good way to think about ground loop heat exchangers is that it's kind of like a battery, right? So a battery can be fully charged up, and then you can discharge that battery and get useful work out of it. And then once the battery is completely discharged, you can recharge it and use it again. A geothermal field is, very much the same type of an application, where in the summer cooling season, you are going to be discharging energy into that field. And then in the wintertime, you're going to be extracting that energy out. In an ideal world, the annual heating and cooling loads would be very balanced, such that for every unit of energy I'm putting into the ground, I'm eventually going to take that unit of energy back out of the ground. And at the end of the year, it's sort of like nothing ever happened. The ground is in sort of a perfect static state. This is rarely the case when we're looking at building designs, especially if you're in warmer climates that tend to be cooling dominated. And that's kind of what the hourly cooling and heating load images that I've shared here are for a region that is going to be predominantly, dominated by cooling. So when the loads don't match up, we call that an imbalanced load. So perhaps you have 4, 5, maybe even 10-to-1 cooling versus heating. Well, how does that impact the design of a ground loop heat exchanger? What it does is it says, you're going to need a much bigger heat exchanger because when you are rejecting all of this energy to the ground, you need to spread it out over a larger area so that you don't cause the permanent sort of buildup of heat within that ground source. So for cooling dominant climates, we're always looking for ways to extract more heat out of the field. One of the ways that we do that is we try to pair domestic hot water heating with these geothermal systems. So you can imagine, domestic hot water requires the extraction of heat energy year round. So during the cooling season, instead of sending energy into the ground, we can send that into a domestic hot water system to try to lessen the load on the ground. Another key component of the design of a geothermal HVAC system is what we refer to as formation thermal conductivity testing. Now, early on in designs, we often use our best engineering practices. We look at other geothermal installations that may have been very close to where the project is being designed in order to sort of estimate how we think the bore field is going to act and sort of what the capacity might be. But ultimately, for any project, you need to do sort of in situ testing at your actual site to understand, what are the actual parameters that I need to design to for my system. There's a lot of things that can impact the capacity of a geothermal field, including, soil thermal conductivity, soil moisture content. You have to look at the underlying geology, whether you have a lot of rock, whether there's a lot of groundwater. All of these things can make significant differences in how your system is going to perform. So this kind of testing is absolutely critical to make sure that you understand what type of geothermal resource you have at your project site. So the next step is to do ground loop heat exchanger modeling. Here I'll use a couple examples of one modeling software, which is called GLE Pro or GLHE Pro. It's a ground loop heat exchanger modeling software. And what the software really does is it takes your load calculation data. So it's looking at your annual heating and cooling loads, the monthly peak heating, cooling, and loads, and you're taking that information and you're effectively entering it in to the ground loop heat exchanger modeling program. Most programs you're able to actually import directly from your load calculation software into the modeling software. So that's sort of a big benefit of being able to sort of automate that process. With the modeling software, you're also entering in all of the ground thermal properties. So these are the properties that you will have been able to receive based on the testing that you've done on site. And then you start to enter in the information about the ground loop heat exchanger. So you're selecting borehole configurations, determining what the borehole diameter is, spacing, the properties for your grout, your piping, the properties for your fluid, you're establishing flow rates, and then you're also inputting specific information about the type of heat pump that you're going to be using. Having accurate information for the equipment that you're going to use is extremely beneficial because not every piece of equipment is rejecting heat or absorbing heat from the heat exchanger in the same way. So the modeling software is quite sophisticated and it can sort of look at the types of performance curves for various pieces of equipment and match that with the geothermal heat exchanger design. So here you see two examples of kind of the information that you can input for the borehole configurations. The top is showing sort of the traditional single U-tube type borehole, but there's also options to do what we call a double U-tube, which is basically like the name implies, you're doubling the number of circuits that you're putting in each borehole. Now, why would you want to do that? a large part of what we're trying to do with the optimization of geothermal fields is, we want to limit the size to be only what we really need for that project. So there are ways to help increase the performance of a single borehole. A double U-tube is one way to do that. Now, I will mention that it is a very iterative process, and we'll talk about that a little bit more. So all these parameters that you're entering in sort of as you approach the first iteration or the first modeling run, a lot of these parameters you may have to go back and adjust based on how the system is performing. So what does the modeling software give you at the end? It'll give you a simulation. In this case, for this particular software, it can do a simulation for up to 100 years of performance. Typically, we're looking at a minimum of 30 years of performance to establish, is this ground loop heat exchanger going to perform adequately over time? It will determine, the number of required boreholes and what depths those boreholes need to be in order to meet your specified criteria. And that criteria specifically is what is your minimum and maximum heat pump entering fluid temperature. So various pieces of equipment can operate at different temperatures. It's very important to establish those parameters early on to get accurate modeling information. In the event that you have a very imbalanced load, so let's say you have 10-to-1 cooling versus heating, loads in your building, the software can also size what we refer to as a hybrid ground source heat pump system, which is basically determining, if I need supplemental heat rejection, how big does that heat rejection need to be to keep the bore field in balance? So the modeling system can assist you with that as well. As I mentioned, it can be a very iterative process. Your concept design of how big your bore field needs to be, your quantity of boreholes, the depth of those boreholes. Once you validate your proof of concept, you may find that, okay, it's not enough, or in some cases, it may be too much. The image that you're seeing on the screen now is kind of representing that imbalanced load that we discussed a little bit earlier. And really what you're seeing is that over time, you're getting a consistent elevation of the ground temperature. Now, in some cases, there is a sort of a range of ground temperatures that may be acceptable. But when you start heating up a bore field over time, you can get to the point where your equipment may not operate. The entering water temperatures may become too high to operate equipment during the cooling season. Or if the entering water temperature is still acceptable, you're going to have decreased performance. So again, one of the things that we look at when we're doing these iterations is, how is the bore field performing, over the long term? So the idea of what we're trying to establish by modeling the ground loop heat exchanger is, how can we get stable operation over a very long period of time? Now, I mentioned earlier sort of your minimum entering water and maximum entering water temperatures. The space between those two things is what we refer to as kind of the bandwidth of the geothermal field. And what we're trying to do is we're trying to optimize how much of that bandwidth are we actually utilizing here. So the image you see on screen, we're operating between about 40 degrees to 90 degrees Fahrenheit, but our minimum temperature is actually down at 30. So this represents, while it represents very stable operation, what it's showing you is that there's a little bit more bandwidth left in this field, and that if there's ways that you can do load management to actually allow the temperature to get a little lower, you'll be effectively utilizing your geothermal resource better. Load management is really, the idea of the hybrid geothermal system, where typically in cooling dominated climates where you're doing much more cooling than heating, load management means that you're adding some sort of supplemental heat rejection to help optimize the ground loop heat exchanger. So what are some options for this load management? Traditionally, you would see sort of an evaporative cooling tower used, similar to how you'd see in a traditional chiller system. You have a cooling tower that's rejecting heat to the environment. Again, trying to be more water conscious and not just energy conscious. Open loop cooling towers can use a considerable amount of water every year. So the industry has advanced with its sort of air source equipment that I'm showing here, which is an air to water heat pump. So you can apply an air to water heat pump to sort of optimize the bandwidth of your system and utilize the ground to its greatest effectiveness. These supplemental systems can also be used to reduce the size of your geothermal field. So if, for instance, you find through the modeling process that the bore field just needs to be bigger than what's actually available on site, you can then supplement that bore field with another piece of equipment to help reduce the size back to something that can actually fit on the site. And then you're kind of having that hybrid approach. Let's talk a little bit about the design documents. So after we've gone through all of the iterations and all of our modeling, and we finally come to sort of a field that we know is going to work for this building, now we have to produce the design documents so that we can effectively have a contractor and a geothermal driller, build this type of system. So those construction documents are typically going to include, a geothermal site plan, geothermal details, very detailed specifications that are calling out all of the different parameters and all of the different materials that are to be used in the system. And then documentation of, the control system, the sequence of operation, how do we think that the system is going to work? The example that I'm showing on this screen is just a small snippet of a very large field, but you can see the kind of level of detailed information that we're typically including in the geothermal site plan. So each borehole is numbered. There's up to sometimes 10, 12 boreholes can be on a single circuit, and then each circuit gets its own dedicated number. And also the site plan is very useful because there's going to be a lot of other things typically on a site that you have to navigate around, whether that's other utilities, whether that's, parts of the building construction. In this case, you see some large rectangles with a keynote 7 in it. That's actually the footprint for the tower cranes that are being used to build the building. So it's important to understand, what portions of the site are going to be off limits for the application of the geothermal system, effectively so you're not counting on having more boreholes and then finding out in construction that it's not a feasible way to install it. In addition to the plan, there's also a lot of detail that goes into, how do we construct one of these? So you're going to have ground loop bore sections that are showing specifically for your project, how that geothermal borehole is supposed to be constructed, what the depth is going to be, what type of grout you're using, the general arrangement. The geothermal header vaults detail here. If I go back one slide, you can see the keynote 2 is calling out where the headers are in the geothermal bore field. And why do we use these? In a significantly large bore field, if you were to run each circuit horizontally back to the building, you would have quite a number of circuits to route. So the vault allows you to take all of those circuits and then simply send 2 pipes, a supply or return, back to the building. So it helps kind of economize on how much space we're taking up on the field. Now that we talked a little bit about the design and how we document the design, I wanted to take a few minutes and talk about, some of the advancements in the industry that are trying to make geothermal, a more viable option on more projects. So we're going to look at a couple things: equipment performance improvements, product innovations, construction innovations, and some unique applications, in this case, a community application. And generally, all of the advancements within the sort of geothermal industry are really trying to achieve the same thing, which is making it more viable for more project types, right? Geothermal heat exchangers typically take up a lot of space, and that space requirement is going to mean that it may not be feasible for a lot of applications. We have a lot of urban applications. Obviously, you have buildings that are constructed in cities. They don't necessarily have all of the space available. So the industry has really tried to advance to make it possible to do geothermal in places that previously it just wasn't possible. So equipment performance, specifically heat pump performance, it basically grows leaps and bounds every couple of years. Manufacturers are extremely invested in trying to improve the efficiency of their equipment. and not just the efficiency, but also the operating range. You can think to, 20, 30 years ago, even air source heat pumps like you would find, in your own home, they did not operate or work very efficiently at low ambient temperatures. That's something that the industry has continued to try to resolve. And now in, more northern climates in the United States, heat pump technology has become viable. There's been advancements in, the compressors that are used. That used to just be that you had a single stage compressor that was either on or off. Now we have high efficiency variable speed compressors that can effectively vary the speed in order to match the exact load, and by doing that, optimize its energy performance. So now we're getting, SEER ratings that are doubling what we were getting 40 years ago. And so that energy efficiency leads directly to reduced energy costs. And so, the less cost, the more benefit over a long period of time. All of these systems now are using advanced control systems that are monitoring all of the data of the performance of each system, and then making optimizations to make sure that the systems are running as energy efficiently as possible. Equipment is also transitioning to low global warming potential, refrigerants. So we're sort of in the midst of a refrigerant changeover right now, where we've gone from traditionally R410A systems that have a fairly high global warming potential to the new sort of version of refrigerants like R32 and R54B, which have significantly reduced the global warming potential of these refrigerants. So, it's important to understand that, while we're trying to maintain energy efficiency, we're also looking at the overall environmental impact of these systems. One unique product in the industry that I wanted to sort of highlight is a product called Twister. So if you remember earlier in the presentation, we were looking at the single U-bend and the double U-bend type borehole. Twister sort of takes that idea and takes it one step further. So instead of one or two loops in a single borehole, this product is actually doing 4 individual loops in a single borehole. It's a product that comes coiled. You can see in the bottom left image, that is a Twister loop, sort of coiled up and ready to be put into the ground. And really, this product is trying to address, one of the main issues with geothermal is, we need to reduce the depth that we have to drill, or we need to reduce the number of boreholes because it costs money to drill every linear feet of boreholes. So sometimes you can address that with a specific product like this that will help enhance the heat transfer benefits in every borehole. The claim by Twister is that they can reduce the amount of piping that you need by up to 30%. And so a 30% reduction can, have significant benefits when you're looking at the overall cost for a project. There's also been a lot of advancements in the drilling technology, right? So one of those advancements is what we refer to as kind of precise geothermal drilling. And really what this is trying to accomplish is that, you're trying to optimize the ground loop heat exchanger and reduce to the greatest extent possible what the disturbance is sort of at the sort of ground level, right? So one of the ways that we've looked at that and the industry has sort of addressed that is with what we call directional drilling, which instead of drilling, completely vertically at a 90-degree angle, the new drilling technology can actually bore at a slight angle, and therefore you can increase the length of a borehole by drilling it diagonally while minimizing the impact at the surface. Another sort of drilling advancement is what was referred to as limited access drilling. And that's kind of the image that you see here on the bottom of a much smaller drill rig. I believe that this specific rig has a height clearance requirement of only 12 feet. And what that means is that you can now drill geothermal boreholes, say, inside a parking structure, right? So you want to drill geothermal boreholes in an existing parking structure, take advantage of that area. The industry has developed equipment that will allow you to do that. And again, it is opening up a whole world of possibilities for geothermal that, many years ago simply didn't exist. Sort of taking on the idea of the directional angled borehole drilling, there's a company called Celsius Energy which produces a system. They refer to it as the Celsius energy pyramid, which you can see in the lower left-hand corner there. And again, this technology is effectively trying to reduce the area required on the surface for a traditional vertical ground loop system by drilling from effectively a single point and then doing directional boreholes in kind of a star pattern from that one location. And again, what that allows you to do is, for instance, the photograph here is that the pyramid is kind of located right in the middle of a park. Well, the park area may not have been sufficient to do a full vertical system, but with this type of directional drilling technology, you're able to get, the boreholes that you need and the capacity that you need in a much smaller footprint at the surface. I also wanted to mention another company called Bedrock Energy. They have some pretty innovative technology in the industry. They effectively are trying to do deep drilling. And the way that they're able to do this is that they've adapted a lot of sort of technological advancement from the oil and gas industry, where they tend to be drilling much, much deeper than our traditional vertical geothermal systems. And again, why would you want to drill deeper? Because drilling deeper means that you don't have to drill as many wells, and you're drastically improving your space efficiency at the ground level with this type of system. So in buildings, say you have a very large building or even a campus of buildings where the load was going to be much too great to have an effective traditional vertical geothermal system, this type of technology allows them to drill deeper, and not only deeper, but they can drill faster than traditional methods, meaning you're using less area, you have less boreholes, and by doing it faster means you're doing it in a more cost-effective manner. And so really that idea of being able to drill deep and drill fast and drill accurately helps reduce the cost of the ground loop heat exchanger, right? And so as the industry advances and finds ways to bring that cost down, it makes geothermal feasible for even more projects. And that's really what we're trying to get after. One of the other unique things that they do is sort of not how they drill, but what they're doing while they're drilling. So they're able to actually put sensors on the drilling rig such that they're getting real-time data as they're drilling geothermal boreholes. Now, I mentioned the testing that we do on each site. Traditionally, you would have one test. It might be 1 or 2 boreholes on a site, and you would get that information, and then you would design the entire geothermal field based on those test wells. Well, in some cases, if you have a very large geothermal system, you may have hundreds of boreholes, and how each one of those boreholes reacts may be slightly different when you start to look at it over very wide areas. So this type of data that you can get from drilling, sort of real-time information for each geothermal borehole, kind of allows for the optimization of each borehole, and it allows for the optimization of the system as a whole. So you could be halfway through the drilling, realize that you're getting better performance out of your boreholes than maybe you even thought based on the testing. And then you can go back and optimize the size of that field. So perhaps you can, reduce the depth that you have to drill to, or even reduce the total number of boreholes. Again, all means to try to, save costs. And they've also found that, their simulation software that they use to model these fields matches very closely with sort of the real world as constructed design. They're typically around a 1% difference between the sort of theoretical modeling and what they're actually seeing in the field. And the last topic I wanted to touch on briefly is the idea of community geothermal. So Interface is working on a project in Austin, Texas called Whisper Valley, which is one of these community geothermal projects. What they're doing down there is very innovative. Typically, when we talked about community geothermal, it would be a community of houses, and then somewhere next to a community of houses would be a very, very large geothermal bore field that you would then be piping to a central energy plant or potentially to each individual home in order to provide heating and cooling. Whisper Valley is very unique in that instead of having one centralized bore field, each home actually has its own dedicated geothermal borehole. And all of the home's boreholes are interconnected together into a very large network. That network is then supported by an energy center that essentially, we talked about load management. So the Energy Center allows for the load management of the sort of community geothermal system. So whenever peak loads are very, very high, obviously in Austin, Texas, it gets very, very hot in the summer. I can attest to that. I've been there dozens of times in July and August, and it can be quite hot. So they have a very cooling dominated climate. So they need the Energy Center to shave that peak off, but then also the Energy Center can be used to recharge the ground during the shoulder seasons when the cooling loads are much, much less. So this is a very innovative design. We're seeing more of these types of applications. And again, it's just opening up geothermal to project types that we didn't think it would be possible to do geothermal in. So with that, I will go to questions. Hopefully we have a little bit of time. Looks like we have about 8 minutes here left for questions. So if you bear with me for 2 seconds, I will try to open up the questions block and see how many of we can get through in the time that we have remaining. Okay. We have a couple here that are pretty long. I might have to reply to that one after the fact. So there's a question about, are there federal, state, or city tax incentives to use a geothermal system in New York? So specifically in the New York environment, I would say yes, we are aware of these types of programs that do exist. The current landscape for incentives is a little bit up in the air. Some of these things have been funded by previous federal grants that some are still going, some are not. Most states do offer incentive programs to either defray the cost of installing a ground loop heat exchanger, or even to the extent to defray the cost of the installation of the heat pump equipment itself. So depending on your local jurisdiction, typically you can go to in your case, it'd be like the newyork.gov website, and they usually will have a listing of what programs are available. So there's a question of, how do you detect leaks and how would you repair them for a closed loop vertical system? So leak detection is often figured out basically, if you start getting very large scale pressure anomalies, you can typically figure out which circuit of the geothermal system you're having the pressure anomaly, and then you can isolate that single circuit. Oftentimes, you're able to actually tell which of the vertical loops within that circuit is causing a problem, and then effectively what you do is you just valve off that portion of the system so that you're not kind of knocking out a large portion of the geothermal system. There's a question about what does the performance diminish over time? So that's a great question. And again, it goes back to the sort of the optimization of the design and kind of taking advantage of the full bandwidth of the field. If you don't optimize during your design and you don't take into account, the 30+ year performance of the field, you can find that it diminishes over time. But again, as part of the design of a geothermal bore field, that's one of the things that we focus on. We have to make sure that we're getting that stable operation year in and year out so that we know that the system is going to work appropriately in the future. There's a question here. Are you aware of any data or studies that analyze the cost and carbon trade-offs of residential ground source heat pump versus electric heat pump HVAC plus domestic hot water with renewables? There are a number of different studies that have been done to analyze these costs associated. Residential ground source heat pumps actually, very interestingly, because residential loads tend to be significantly less, what you'll find is that these systems are actually paying back even quicker because the number of boreholes that you typically have to drill in a residential application is going to be significantly less than a commercial application. Also, the loads are less. But there are a lot of trade-offs. Again, there's been advancements in air source heat pump technology as well. So, each sort of condition has to be assessed on itself to figure out, which is going to be the most effective. I think we got time for a couple more. So there's a question about what would the upfront cost in percentage compared to a traditional system be? It's always a tricky question. I will say the one thing, as someone who designs geothermal systems and has multiple geothermal systems installed within the last few years and also being installed currently, there has been a pretty large variation in the cost for geothermal if you look at it from a sort of dollar per foot standpoint. So it is difficult to say, a definitive kind of percentage, but I would say if you were comparing a traditional, say, air source heat pump system to a geothermal system, there's going to be a significant upfront cost, but the payback period, it might be anywhere from 5 to 15 years, depending on how much you're paying for energy. So geothermal systems really are the type of system that you kind of have to look at like a longer time span because they are going to last for so long. So you may not get that immediate payback, but if you're going to own the property for some significant period of time and you can look at longer payback periods, it does make it, that much more feasible. There's a question here about, is there a rule of thumb assessment for building size versus the number of geothermal wells required? The answer to that is yes. However, like I mentioned previously, you have to be very, very cautious about these rule of thumbs. It is handy to have a rule of thumb assessment because, again, if you're trying to very quickly determine the viability of a system, you kind of have to jump in and say, like, okay, I have a home that's X size. Like, how many geothermal boreholes might that be? Oftentimes, the rule of thumb is to calculate, okay, if you have a home that is 2,000 square feet and you are averaging, let's say, 500 square feet per ton, that means I have 4 tons of cooling. So for that area, how many tons of cooling am I getting out of a geothermal borehole? Maybe it's 2 tons for a 500 feet deep borehole, right? So you're like, okay, I need 2 geothermal wells. Again, that's going to give you an order of magnitude what your system might need to be, but doing the precise load calculations is always going to be critical for understanding kind of exactly how a geothermal heat exchanger is going to work for your project. There's a question here as well, and I think we have about 1 minute left, so I'll try to get as many as I can. Outside of space heating and cooling, are there other applications within a building that can be part of a geothermal system? Domestic hot water heating or pool water heating? The answer to that is yes. Effectively, anything that needs heat inside of a building, whether that is processed hot water for, say, a hospital application where you are continuously throughout the year generating hot water, you can tie in other water source equipment to the geothermal loop to extract that energy out of the loop and help balance out your fields. And with that, I think we are at about time. I will have to review everyone else's questions and get you answers afterwards, but I wanted to say thank you for participating in today's webinar. I really appreciate everyone's time. And before we get out of here, I just want to let everyone know that there will be another presentation as part of the webinar series next month called Building Electrification, the End Game. And this is going to be done by some of our partners out on the West Coast. So thank you all again for attending, and we look forward to seeing you at our next webinar.
Great job, Joe.
Thanks, Joe.
Thank you. Thank you, everyone.